So I guess to talk a bit more about stability, there are two options. One is either I could start with theory or start with another example. So maybe I'll start with theory this time instead of starting with the example. So here is the example is the L96 code that I had sent. That's already there. So if you get bored of the theory, then start playing around with the notebook. Hopefully it runs. That one I'm a bit uncertain about. But actually, sorry, before I erase all of this, two things I left out. One I didn't even mention at all, and the other one I said I'll talk later. Alpha, which is called inflation factor. So let me go back to the code, and then I'll come to the board, which is, where is the code? There, the highlighted piece over there, right? So when calculating the covariance, so alpha is a number which is close to 1 but slightly larger than 1, and that's a usual choice. And that's why it's called inflation, and we'll see why. The covariance is basically a computation that looks like this, right? It's this multiplied by its own transpose. That's the covariance. If I multiply the whole object, every ensemble member, every component of it by some number alpha, so I put a alpha in front of this, the covariance will get multiplied by a factor called alpha square. So this will get multiplied by alpha square. This is the additional bit. If alpha is larger than 1, this will be larger than what it will be without alpha. So the covariance, each element, or basically the eigenvalues of the covariance, which are the variances, so which are not necessarily the variances, sorry, which give you the uncertainty, will be larger as compared to if you don't use the alpha. Of course, if you use alpha less than 1, then the variances will be smaller. Yeah. So usually alpha, which is larger than 1, is what is called inflation. And this is another way to fix basically the same problem. Remember what was the problem with filter divergence without the use, without the perturb obs? Without the perturb observations, we basically do not have this term. We are consistently underestimating the covariances. So the ensemble is becoming precise, but inaccurate, and then the filter divergence happens. One of the ways to fix it is to just say that, oh, let me just increase the covariance artificially. And this is that artificial increase of covariance. Just multiply the whole covariance matrix basically by factor alpha square. When you multiply the ensemble by factor alpha, that multiplies the on the matrix, the covariance matrix by alpha square, that's larger than 1. That increases the covariance by some small amount, and do it consistently at every time step. The covariances, you are basically making them slightly larger every time step. And that kind of prevents this behavior of becoming smaller and smaller and smaller eventually. So we could, this is very sensitive, extremely sensitive. So, okay, two things. When adding this with a right covariance, that's a very systematic way of increasing the covariance, because we know what the factor is. It's KR, K transpose, which is exactly what we want. So we have a good control over what this number should be. When we simply multiply by some small number, small, close to 1, but slightly small, larger than 1 number, it's not really a controlled change of your covariances. And so there's a lot of tuning that needs to be done. 1.05 may make it too large. And what do you mean by too large? The ensemble simply becomes extremely uncertain. Now we know where to look for. What do we mean by ensemble becoming extremely uncertain? The weightage given to the ensemble will be small. This factor will become small. This factor will become large. The observations will get much higher weight. The ensemble will get smaller weight. The limit of PF goes to 0 was kind of straightforward to see, right? Because what we have here is essentially PF goes to 0, that term goes to 0, so there is a R inverse. It's a non-singular limit in some sense. There is a PF here, so PF, which goes to 0 anyway, times something that does not go to 0 because there is a R here. And so everything, the K goes to 0 is a slightly easier one to understand. What happens when PF goes to infinity? So, I mean, becoming large always doesn't necessarily mean going to infinity, but let's just take this extreme case of PF becoming very, very large, going to infinity. How do you take the limit of PF goes to infinity now? Okay, that's a bit tricky, right? PF goes to infinity basically will mean that inside the parentheses, this term will dominate, this term will be large, that term will be small, so that goes to 0, basically, or the other one way to say it is that is very, very small. If that is very small, you're taking the inverse of this, but this is not a square matrix. So now you have something that's very large, infinity, times the inverse of something that is also infinity. Okay, so that's a very tricky limit to take. But you can do the mathematical tricks, and I'm not going to go through the details. Essentially, it will turn out to be this term going to becoming small, and this term becoming finite. So that limit actually happens to be finite. K is finite. K doesn't go to infinity. Anyway, so so that's the outcome of all this, and that means that the observations get all the weight in this linear update, and the ensemble is neglected. So that's not a good thing either. So if alpha is too large, then that's what will happen. If alpha is too small, and we don't have the perturbobs, then you know what happens, because everything just collapses. So the tuning of alpha is tricky, is very tricky in fact. So, and then you can come up with all sorts of tricks like, should the alpha depend on time? You can maybe tune, you can increase for some time, decrease for some time, this and that, or you can change alpha from a number to some vector so that some components of xi are inflated larger by larger amount than some other components, this and that, adaptive inflation. There are lots of things that can be done, but the basis of it is all of this. And that tuning is kind of complicated, so, but there is an easy way to play around in this code here, which is, if you just set that parameter alpha, which already, by the way, so I guess without saying anything much about it, I had already set alpha to be non-zero. So inflation was already happening in the background. I didn't say anything about it, but okay. So so try now setting inflation to 0 with the, so we know what will happen if you set the inflation to 0 and the UIs are set to 0. Then clearly we know what will happen. There will anyway diverge. That's for sure. Now set the UI to be 0, but can you just play around with alpha by itself and get the filter not to diverge? What do I mean by filter not diverging? The ensemble covariance should remain finite, something that's reasonable. The filter should not be too sure of itself, so sure that it's completely lost track of reality. That shouldn't happen. So that's the main goal. Yeah. Okay. So play around with this. I'm not going to do it right now. That tuning is very, very tricky. I mean, very meaning. You literally have to do this. Set it to 1.1. It will blow up. Set it to 1.01. It will collapse. And now maybe do a binary search. I don't know. Whatever. Okay. So that's the inflation.
That is very suspicious. What amount of alpha we should keep?
It is.
Right now, you are using 5%.
5%, yeah, it's basically 5% inflation, yes. How much should be used? No.
Would you like to give us insight how to decide?
I don't have any. I have never in my life ran a real world ensemble Kahneman filter application. Okay, not true. I've done it for ocean models long ago, but it's tricky. It is very, it is application dependent. Atmosphere, ocean will be very different for each other. Ocean dynamics is very slow. So dynamical aspects come in. I don't want to discuss the details of how they come in and all that. But I'm not the right person to ask or answer this question because I have never done it in practice. I don't have any insights to give you. Okay, so.
We have to do a lot of experiment by changing the values of.
Yeah, yes. I will, rank of P? Yes, I will. I will come to that. Yeah, I'm coming to the rank in a minute, yes. So this is an ad hoc fix, right? That's pretty clear. That using inflation is ad hoc fix, but it is. I mean, there is a lot of ad hoc bits of ensemble Kalman filter that go way beyond the theory. And in fact, there is no good theory behind choosing inflation, and hence it's a tuning process that for which I do not have any insights per se. Okay, the theoretical understanding is clear. You want to keep increasing the inflation, the covariances to be non-zero or finite, and that's one bit. The second bit, to talk about that, okay, so maybe I will, sorry, I made a choice. I will run the notebook first, and then I will talk about the theory, the stability, and so on later. Okay, where is the notebook? The L96, the Lorentz 96 equations. These are equations of this following form. There are n variables. In this case, n happens to be 40, 0 through 39. The little n is 40 in this case. And those variables are x1, x2 up to xn. And those are the equations. So there is a quadratic nonlinearity, xi minus 1 times xi plus 1, and xi minus 2 times xi minus 1, dot, 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 and so on and so forth. So that's just it's not that different looking from the Lorentz. It has Lorentz 63 also has quadratic nonlinearity. This is quadratic nonlinearity, except that now you can think of this as, so what happens when I equal to say 39? What do you mean by I plus 1? I plus 1 now for I equal to 39 is 0. So it's kind of like a circular. So think of this as a mod. I is an index that's mod 40. So if I equal to 0, then I minus 1 is 39. If I equal to 0, I minus 2 is 38. So think of these as in a circle, right? x0, x1, x39, and then plus 1, plus 2, minus 1, minus 2, and so on and so forth. Yeah? So that's how you can think of those variables. Okay, so just a equation with 40 dimension. Everything else remains the same in terms of process. So if we let's go through. This is the same. The equation is defined. The code is over here. Model dimension in this case now is 40. The generate trajectory code remains identical, except that I have changed the style. Okay, wait. I think time is anyway. Yeah, the time steps. Actually, maybe the time steps are the same. I don't remember now. Anyway, so it will go from time 0 to time 75, and now generate a trajectory. It's working. It's 40 dimensional. It takes significantly longer time, and we can see how long it is. It's 750. So it's 750 observations, separated by capital delta of I think 0.05 or something like that. Anyway, and then we can plot what this looks like, and this is one of the solutions. Okay, exactly same idea, generate observations by multiplying by the observation operator, add some noise. You control the amount of noise by setting the observational covariance. And so mu equal to 0.7 is the standard deviation of the observational noise. It will be diagonal in this case. There are a couple of choices that I have set up. One is you observe every alternate coordinate. So coordinate number 1, 2, 3, no, sorry, 1, 3, 5 or something like that, or maybe it is 0, 2, whichever, odd or even coordinates. The second choice was that you choose the dimension of the observation, say 20, or you could even do 5, for example, and choose 5 random coordinates to observe. So the permutation of this matrix will basically give you a random coordinate to observe. Python trick, but so let's go with random for now. Okay, so I will do this, and I hope it's going to work. If it doesn't work, then I'll go back to observing alternate coordinates. And maybe 5 is too small. I will do 20 observations. So it's a 40-dimensional system. If you observe too little, there are problems. If you observe too much, Are there problems or not problems? Actually, there are. We'll come. Okay, so that's a slightly more difficult thing to understand. Why should too many observations be a problematic thing? But anyway, so it is also in fact a problem. But for now, I'll choose random observations. So that's the code for random observation bit. Add the noise, blah blah blah, and so on and so forth. Okay, so there is a bit which is wrong, which is should have been obsdim. Okay. Yeah. And if you want to see which components have been observed, this is a small piece of code that will just list out that the first observation corresponds to the second component, the second is the 17th component, dot 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 all the way down to. Right? So it will list out because it was randomly observed, so I need to know which one I am observing. And observation should be 20-dimensional. That's just a check. I can plot the solution. Oh, fourth component is not observed, so I can't plot the observations on top of it. So let me choose, let's say, the 12th component, which was observed. Oh, sorry, off by 1, so this should be 11. Okay, so, wow, that's a lot of observational noise. It may fail. Okay, so I don't know if it's going to work or not. We'll figure out whether it fails. The same set of parameters, the same similar kind of set of parameters, initial bias, initial covariance, step size, this and that. I have set alpha equal to 0. Okay, I'm going to not go with alpha equal to 0. Maybe not a good idea. So let's go with alpha non-zero. And I don't know what's going to happen. We will find out. Right? Ensemble size is still 100, fairly large ensemble size in this case also. Now there is this additional bit called localization. I haven't talked about localization, but in this case, localization, keep that word in the mind, I'll come to it in a minute. So localization is said to be true for reasons which right now are mysterious and so on and so forth. And once having set all these parameters, I will go ahead and generate initial ensemble, which will have a bias, which will also have its own covariance. These functions are identical. The model forecast and analysis has been done using the same code, exactly identical code, with the perturb observations as well. And now just run the code. This does use the perturb obs, right? So R is not multiplied by 0 or some small factor, anything. So this is perturb observation ensemble Kannan filter, identical to what it was for the previous case. This will take a little bit of time to run. While it's running, here is the exercise. This was a literal translation. This bit of code here is a literal translation of the equations over there, right? It's just looking at each piece and just compute the whole thing as is. I also wrote an expression for PF, which is like this. If you substitute this, what happens to this expression? There is a slight bit of difference, so I will erase the dimension and I will write it below. Yeah. So let's just put this in here and see what this comes out to be. Right. So K is equal to PF is ZF, then ZF. Sorry. I anticipated what's going to happen. Right? It will be ZF transpose times H transpose. I combine the H transpose, ZF transpose, H transpose and write it as H ZF transpose. Times, there is a H and ZF. So there is a H ZF. Then again a H ZF transpose plus R inverse. What's the dimension of PF? N cross N. For high dimensional model, this is a large matrix. What's the dimension of ZF? I wrote it somewhere. Oh, it's here, n cross n, right? N cross p, p is the ensemble size. So if this is very large, in this case, of course, our case is different. We are dealing with very small dimensional models for now. But if this is very large, the ensemble size is typically 10, 50, 100, something like that. Then this matrix is clearly much smaller dimensional than this matrix when n is quite large. So ZF by itself is small, not very large. What is H times ZF? What does H do? H takes you from the model space to the observation space. If the model space is dimension n, H times ZF will take you to which space? The observation space. So that should be m cross n, and that's easy to see. So H ZF by itself is m cross capital N. M is the number of observations. N is the ensemble size, right? So this is also a smallish matrix, not as big as n cross n matrix. So everything here now is not a very large matrix. There is nothing n cross n in this equation. HZF is m cross n, this is n cross n, n cross n, and so on and so forth. So I don't need to actually compute such a big matrix, which is the covariance of the forecast ensemble. The covariance of the forecast ensemble is not needed to be computed at all. It's very large for large dimensional matrices, and we don't need to compute it. All we need is H, ZF, and ZF itself. ZF is basically just the column, so you can take the ensemble. By the way Python is arranged, forecast ensemble, if I remember correctly, it's the exact dimension of ZF, or maybe it's the ZF transpose, one of those two. Oh, sorry, the mean is not subtracted, sorry about that. The ensemble forecast matrix there in Python code is basically just these columns. So you have to subtract the mean also to get ZF from that. But the dimension is either n cross n or its transpose, capital N cross little n, one of the two. I forget which one it is in that case. And so this computation is actually straight. In fact, even this computation is very easy to do in the Python code. This is exactly the ensemble covariance, sorry, the forecast ensemble variable, but you have to subtract the mean from each column. Remember to subtract the mean. HZF, that's straightforward to compute, and then that's all that is used. So try to rewrite that code to use this, translate this into a code rather than translating that into a code. This is much more efficient in terms of, for large dimensional systems at least, yeah? Okay. So that's one bit of, in fact, there is another trick. We have talked of two spaces. Varun talked about two. I didn't really talk of two spaces too much, which is the model space and the observation space. Now, actually, there is a third space, which is the ensemble space. The space spanned by the columns of the ensemble matrix. So the columns of the matrix that will contain these vectors as column. So each of the vector here is a little n dimensional vector. There are p, I'll now go back to using p as ensemble size. There are p such vectors. And let's assume that we are working with very high dimensional system, n is 1,000,000 or something like that. We have p, which is say about 100, the ensemble size. The 100 vectors in a 1,000,000 dimensional space will span a 100 dimensional linear subspace. And that linear subspace is called the ensemble space. So the ensemble spans a much smaller dimensional subspace in a very large dimensional model space. That's a usual application, right? And so there is a third space now to deal with. The ensemble does not span the whole of model space, but it only spans a subspace of dimension p, and that's called ensemble space. Question for you. In our setup, in this Lawrence 96, when little n is 40 and capital N is, or p, is 100, what's the dimension of the ensemble space? The space spanned by the ensemble members. What I talked about was if little n is 1,000,000 dimension, you have a 1,000,000 dimensional model space, you have 100 ensemble members, they span a 100-dimensional space within that million dimensions. What is the dimension of the space that spanned in this example? I want a number, integer, preferably integer. It's a dimension. Sorry. Wait, come on. You. Terrible joke, is it? Okay, anyway. What's the dimension of the ensemble space in this case? 40. Why is it not 100? Yeah. Yeah, so let me maybe try to rephrase. You said it, but the mathematical rephrasing would basically be the following, which is that the ensemble space is always a subspace of the full model space. In this case, the model space is 40-dimensional. The ensemble space can only be a subspace. It can be up to 100 dimensions, but a subspace of 40 dimensions cannot be larger than 40 dimensions anyway. And so basically the ensemble space in this case is actually equal to the 40-dimensional subspace, as long as there is not too much redundancy in the ensemble members. If there are multiple ensemble members which align, okay, that shouldn't happen, because anyway they are generated randomly. So that will not happen with probability 1, and hence they will span the whole of the ensemble space in this case. Usually for very high dimensional examples, that will not be the case. So this matrix will have a dimension of n cross n. The rank of this matrix, by the way, okay, so let's talk about rank. So sorry, I was coming to the rank here, which is that, look at the columns of this matrix. They are xi minus x bar, right? So what is the sum of all the columns? When you take the sum of all of these columns, so you sum over I goes from 1 to p, sum goes from I to p, minus this sum, so that's n times x bar. The sum of I goes from 1 to p of this object is exactly n times x bar as well, so it's 0. So the column sum is 0. So the rank of this matrix is capital N minus 1. Or little n if little n is smaller. So it's the minimum of little n or n minus 1. In high dimensional problems, little n is very large, so it's always going to be n minus 1. So 100 ensemble size 100 in a million dimensional space will give you a matrix ZF which has a rank of 99. A 40-dimensional model space with an ensemble size of 100 will give you a ZF which has a rank of 40. Yeah? So in this case, the rank will be 40. In the usual high-dimensional examples, the rank will be 99. I'm fixing the ensemble size to be 100 for now, for discussions, yeah? Okay, so that's the rank of this. The rank of that is identical. What's the rank of the sample covariance? It cannot be larger than the ranks of these things, so it has to be basically equal to this object. In our example, the rank will turn out to be actually, sorry, my mistake. Rank will be less equal, so, okay, so I made one mistake, which is that the rank of ZF is less equal to this object. It may not be equal to that. Hence, the rank of PF is also less equal this number. Yeah? So in this case, since the ensemble size is sufficiently large, 100, basically the rank of this can be up to 40, and that's possible. Yeah? So basically that's called a full rank matrix. Rank PF is a n cross n, 40 cross 40 matrix. It has a rank equal to 40. If it has a rank equal to 40, that's called a full rank matrix. So in this case, we will be able to, at least in theory, get full rank matrices for covariances. In practice, that will not happen, of course, because if n is large and this is small, then the rank cannot merge. So you can only capture 99 non-zero eigenvalues, and all the other eigenvalues will be 0 for the covariance matrix. Okay, so I was saying all this because of actually something else. So these objects here, right? So what we, let's run this first and then I will come to that later. So efficiency, we can make this more efficient, and now it has stopped, running has finished, so it finished the run. Let's just check. The sizes are okay. Component 7 was observed or not, I don't know. What components were observed? Actually, it will, oh, 7th, so 7 minus 1, so 6. I should put 6 so that I get an observed component. I think this is a counting problem. Oh yeah, comp by 2. Why is it? Sorry, there are some mistakes. I realized that the one I uploaded, there are some mistakes. I don't know why this is comp by 2. This should have been one more mistake, huh? The observations of this trajectory, the one in green, cannot be the dots over there. So there's some counting problem in the way the code is written. Sorry. Oh, what you have works out correct, is it? Oh, so maybe I did not apply. Yes. Yeah. No, alpha, the observations have to be around the trajectory. So there is a problem with the plotting of the components. This is just a purely plotting problem. I think I know. Yeah, I got, sorry, this should have been II. You get it right? Yes. I know why you get it right, because you are working with the code, the way it was written, the code was written, it was written, it was hard-coded, this part of the code was hard-coded for alternative observations. When the observations are not alternate components, I'm choosing random components to be observed. So I need to match the randomly observed component with the trajectory. This is just purely Python problem. Okay, so Python is, I'm not going to discuss Pythonese with you guys right now. So anyway, match the components properly. So it should have been this part. When in the plotting, this should have been II in that bit of a code. Do you see, for the plot, do you see this? Which is for II equal to NP arranged obsdim. Is that in the plotting code or not? In the uploaded notebook? Or did I add this afterwards? I don't remember now, sorry. There was a bit of a time lag between what I uploaded and... the plotting part, the plotting of the trajectory, does it include these two lines of the code? It does. Okay, so if you change this to II, then it will work fine. I'm pretty sure of that. So these are the observations and these are, yeah? Okay, so now we can just plot the error. Right, the error nicely goes to 0, so the filter is working. This is actually a working filter, amazingly enough. And now we can go ahead and compute the covariances of the forecast matrices. So here are the covariances. The eigenvalues can be computed. I'm plotting the covariance. Okay, so this is something else. And now I can plot the covariances. Is this the plot? Yes. Okay, so this is the plot of the eigenvalues of the covariance matrix as a function of time. Let me not plot it up to time 1000, maybe a little bit less, so that slightly better visibility. Yeah, okay. So you can see that all the eigenvalues start off being order 1. close to 1, right? This is semi-log plot. So the eigenvalues are close to 1. Some of them stay close to 1. Some of them become smaller and smaller and smaller. So eventually, quite a few of them are of the order 10 to minus 4, which is close to 0 numerically.
This is 40 and capital N is 100.
Yes. Yeah. Full rank. Yeah. The full rank is, yeah.
Can you flip it?
I'm sorry?
Can you flip it? You make the smaller N 100
It will take time to run. I will flip it at some point, but yes, yes, but anyway, so the point is, look, the eigenvalues, not all the eigenvalues remain large. Some of them, in fact, become small. We said that the rank can be 0. Oh, by the way, when the rank is less than the full rank, if the rank is less than n, then some of the eigenvalues will be 0, equal to the dimension minus the rank. That many eigenvalues will actually be 0. And that is numerically the case here. There are many small eigenvalues, close to 0 eigenvalues. So in principle, it can be a full rank matrix, but in practice, it actually turns out to be not full rank. Some of the eigenvalues, in fact, do go to 0. What are the eigenvectors corresponding to that eigenvalue which has gone to 0? What is the interpretation of that? And that, I guess, that's part of the stability results, which I will hopefully have time to talk about. Okay, so yeah, is that clear? If you want, we can flip. Should we flip? So a couple of things we can try to do. You can try to make it fail by, of course, so before flipping, I can try to fail and then see what flipping works. So but what you are asking is the following. I talked about the case when the ensemble size is larger than the dimension of the model space. What about that's not the case? So should I try this on the fly? Why not? Let's do this. Okay, so 100-dimensional model. Very skeptical, but let's do it. Okay. And generate a trajectory. That part remains identical, no change in the code. I generate a trajectory. It's already taking quite a long time. And shape is now 100. And this looks good. This is the same. I will still observe 20. I'll keep observations to be, actually I can make it 50, why not? Okay, half the components will be observed randomly. Which half? All of these, 55th, 19th, 95th, dot. And let's see how the plot looks like. So similar. Oh, again, there is a problem with the index, which is this should be II. Now the observations are around the trajectory as they should be. Sorry, so those two places where I'm plotting the trajectories, please change that index of this bit. Yeah? Don't rely on this, the number 43 here. This is probably 400 and something. After having run multiple times. This is the number of the counts of sales that have been done. So this is, okay, anyway, so after changing it to II, this is correct. And now this looks like the trajectory. I will make the ensemble size to be equal to, where is the ensemble size? Capital N, to be 40. Good? Or actually, I would make it 60. I don't know how many positive Lyapunov exponent this one has. So if it's not sufficient, then this is going to fail pretty badly. So okay, so I'll make the ensemble size to be 60, still less than the model dimensions. Hopefully other things will look okay. The localization seems fine. I haven't talked about localization, so you have no idea what I'm doing, right? Oh, why is this N? This should have been model dim. Okay, now it's working. Sorry, there are little bits and pieces. So there is a the the covariance matrix for the initial ensemble was using little n, and right now little n is not a variable, unfortunately, in this code, but anyway, so, okay. Oh, or little n was set to be, I think, maybe 40 or somewhere, something like that. Okay, so this should just be as it is, should just work. This is where changing that bit of code to the bottom line, which is more efficient, may be useful because the runtime will change significantly now. If I don't do that, the bottom line, then the runtime will be larger because I'm multiplying large matrices for no reason. I should really be using the efficient way of doing it. But anyway, for now, let's just go with it. And if I run, this will take a long time to run, but let it keep running in the background. R is wrong dimensions. Why is R wrong dimensional? Where did R go? Oh, R was, again, little m was a variable that was earlier used and now it is not. This should be obs. So the observational error covariance matrix R should be, of course, the dimension of identity, right? I. And this should be mu. Okay, so now hopefully it will run. Hopefully it has correct dimensions. Why is it still wrong dimensions? So something was hard-coded for 40 dimensions. What was hard-coded for 40 dimensions? Sorry about that. The code shouldn't be written like this. Code should be written so that they are modular. Oh, yeah, the n, little n here. Yes, of course. So this should be model dim. This n should be model dim. This n should be model dim. Okay, there. I hope now that is okay. Yeah, now that's 100 cross 100. Initial ensemble, this runs like that. Hopefully no more dimension problems. I think it is running now. Okay, let's see what happens. Sorry about it. Well, no, my code was not modular. That's the problem. There were things that were hard coded, and I forgot about those. So anyway, it's running now. So let's come back to looking at the result. Oh, it's done. No, it's done.
The point I wanted to make was
yeah.
the inflation factor. The application of the inflation factor will differ between the two cases.
Yeah. Oh yeah. The inflation. Yeah. So it actually is working well. This one ran properly. So now let's look at. Okay. So where are we? I ran exactly identical experiment. The only difference was 100-dimensional model. The same inflation factors seemed to work okay, magically. I don't know why, but anyway, so it's okay. And 40-dimensional ensemble. So the ensemble size is smaller. So PF. So what do you expect the rank of PF to be? The ensemble covariance. N is now 100. Capital N, ensemble size is 40. So you expect the rank of this to be? Sorry, it was 60, sorry, 60, okay, fine. This was 60, not 40, but 60. So you expect the rank of this to be equal to? 59, thank you. Subtraction by 1 should be, okay, so there you go. Here is the computation of this. So even at time t equal to 0, we can see that there's a whole bunch of very small eigenvalues. Right? And so if I make the plot of what the eigenvalues actually look like, look at that. So I can't even count, I can't count these number of lines. But everything that's below something like 10 to minus 10 is numerical 0. And that should be so the rank should be close to 59 or maybe 59. So all those, there should be 59 lines over there. And the remaining 41 lines should be basically 0. So you can do this counting, please. Yeah. So count the numbers that are less than, yeah. "41. I just counted how many eigenvalues are less than 10 to minus 10. And that's 41, right? So, okay, fine. So,
Hey, the program works very well.
the program works well. There you go. So, yeah. Control C. Just 1 second. Give me a. One last bit. Control Z.
Your R is full rank, right? Maybe it's R.
R is full rank. Yes. In this case, R is full rank. Yeah.
All the responsibility in inverse computation.
Yeah. Yeah. Sorry, of course I can't, okay, so this I can't do. Anyway, fine. So, where were we? Full rank matrices, if the model dimension is smaller than the ensemble size, if the ensemble size is smaller than the model dimension, then you will not get full rank covariance matrices. Some of them will be zero sheerly because you cannot represent all the directions in the model space. This has nothing to do with dynamics. It's just purely algebraic inefficiency, deficiency, whatever you want to call it. Even in the case when your possibility of getting a full rank matrix with the model dimension being smaller than the ensemble size, so sufficiently large ensemble size, larger than the model dimension, there is a possibility of getting full rank matrices. Some of the eigenvalues actually end up going to 0. They don't start out by being 0, they decrease in time, they go to 0. So what's a picture of a matrix that has 0? So so you can visualize covariances in terms of ellipses. The semi-major and semi-minor axis give you the eigenvectors of ellipse, or eigenvectors of PF, and the lengths of that, the semi-major and semi-minor axis actually, sorry, the directions give you the eigenvectors and the lengths are the eigenvalues. So if this is a if this were a 2 by 2 matrix with rank equal to 1, the uncertainty ellipse corresponding to that matrix will be not a ellipse like this, but that. In one direction, the width of the ellipse is 0. In the other direction, the width of the ellipse is non-zero. That's eigenvalue of that value. Yeah. So essentially, they flatten like pancakes in some directions, like dosa, and still retain the shape in the other directions. Okay. So why does that happen? Stability. So this has to do with dynamical stability. The reason why some of the eigenvalues go to 0, even in the case when they should not actually be going to 0, has to do with dynamical instability, and for that I need to talk about instabilities. So I will talk now about what do you mean by unstable dynamics. Questions up to now? No questions whatsoever? Wait. What?
The modularity of your code, in case you want to change the thing.
Do I want to? Do I want to talk about something that does not exist? My code is not very modular, but anyway. So, okay, so the way you can play around with this is as follows. Let me just quickly go through the places where I think now, so I changed it so that now hopefully it is pretty much, I will upload this code, the one that ran perfectly fine, even with changed dimensions and changed ensemble size and so on. I will upload that on the Google Drive and send a link and so on. But before talking about modularity of the code, a part that I was pushing under the carpet. I said I didn't talk about it at all. Localization, keep it in mind. And now let's talk about localization. So, wait, what? Where is my, no, sorry. I thought I had the file open which showed the, okay. I don't have it, sorry about that. I thought, I didn't plan this properly. The idea behind localization is as follows. What does covariance matrix tell you? It tells you a relation between different variables in terms of just correlation. Just at a linear level, the correlation between different variables. If you expect a correlation, so the example I was going to try to show, which I will show later. Okay, why don't I do this? Why don't I talk about stability now, since we are anyway about this, and talk about this once I get the proper set of slides to show you the localization bit. And modularity of the code also later.
I heard several people telling what was model. So if they are planning to do ensembles,
don't use this code for no, this is not a code for anything beyond say 50, 100 dimension, 200, this will take you a million years to no, this is not efficient, this is not a computationally efficient code. It's just a hack in the sense that it works sufficiently well that you can do simple experiments. You can try to understand what this code is, but not to actually use it for operations. I mean, that requires a lot more work than, yeah, no, this will not a great idea. For example, one thing it does not include is, for that I need to talk about localization, but anyway. Localization I have not talked about, but for example, it does not have any clue about how to localize, say, temperature at this point and temperature at that point versus pressure. And so if you have multiple variables at the same spatial location, this code has no concept of that. So no, this is not for production runs. Yeah, this is a purely research code and not a production code. Okay, as you may have seen, so many typos already in the first place. But
if the person working in toys or aircraft, they have a walk model running.
Yeah.
And they have some observations, a new set of observations. If they want to write a data assimilation module to add to that, how would you structure the code? That's what I thought you may want to do.
Okay, so maybe what I can do is I can try to. I will talk about this in the afternoon. I don't want to do it on the spot and make mistakes, and which I will. Not that I will not make mistakes in the afternoon after having prepared, but the chance is smaller. So I'll do it in the afternoon then. Yeah. No, not right now. Yeah. Modularity in that sense, that's what you mean. Okay, but just coming back to this code quickly, most of the things should be now easy to change. So what are the things that you can play around with? What are the so to say parameters, hyperparameters that affect assimilation? Let's start from the very beginning. Of course, the model dimension, that's a big thing, right? The high dimensional models, things will be much different. That's a hyperparameter. Something I did not pay any attention to. Time between observations. The longer you wait between observations, the more nonlinear the model in some sense becomes. I don't have a good way of justifying this right now. I didn't talk about nonlinearity in any great detail. But if the time between observation is too long, what is too long? I don't know how to say what is too long. But if the time between observation does affect the quality of the assimilation, so that's a parameter you can play around with. Do a run, everything else identical, one with small time between observations, another one with slightly larger time between observation. Is there a change? Can you make it can you go from say 0.05, which is currently the time between observation, to say 0.2, which is 4 times the large time between observations? What will happen? So that's one hyperparameter, right? Yeah. Do I need to write it down? Can you please write down what hyperparameters are instead of I'm making a list? I don't want to make a list on the blackboard now. Okay, so one hyperparameter, time between observations. That you can play around with. So it's this one, dt, right? And because the code is not so nicely written, there is another place where dt goes, which is so I should have, okay, so what I should really do is somewhere in the top, say t obs or something like that, and use that as a variable in multiple places. So this obs gap that is mentioned over here is also that same number. So if you change that to a variable, that is probably a better way to do it. So maybe at the top, make a list of hyperparameters and then use them as variables somewhere in the code. That will be a better way to do it. But anyway, so remember, if you change the obs gap, the time gap between observation, change it at 2 places. Okay, that's one thing. Observational noise will clearly be an important parameter. If you have very, very highly noisy observations, the effect of that will be less than having more accurate observation. The accuracy of the observations, the precision of the observation should be important. So that parameter, as I mentioned, was the mu. And as I said, the mu, I think, has been not written properly as a parameter, but rather actual numbers in a couple of places. So search for the mu and change it at appropriate places. Where is mu in this case? So this is the observational standard deviation, right? This was 0.7. What if you make it 1.5? What if you make it 0.001? Maybe not, don't make it so small. Actually, try this. You would imagine that if you make observational noise to be very small, things might be better because your more precise observation better. Not so easy, but I'll leave it to you to take care of that. Of course, the number of observations should matter, the observation dimension. I took half the system size, model dimension was 100, observation dimension is 50, I'm observing 50 of the 100 components. If you only take this to be 3 or 10, so you're only observing 3 of the 100 components, what happens? That's another parameter to change, right? Of course, which observations will have more effect? So if you take 3 observations which are component 1, 2, 3, as opposed to 3 observations which are component 1, 15, and 35, is there a difference? I don't know the answer to this actually at all. Right? So which observations matter more and which observations matter less? That's a hyperparameter in some sense. Observational noise, time between observations, ensemble size. When you are doing ensemble Kalman filter, the size of the ensemble will matter. If you take the ensemble size to be 5, probably things are not going to work out well. If you take it to be 100, of course the computation time will go much larger, but it hopefully will work better, and so on and so forth, right? So what's the dependence on the ensemble size? That's something that you can play around with this code.
Sir, suppose if I am taking 5 numbers.
Okay.
And in another experiment I am taking 100. One is very large and one is very small. So in order to do computationally efficient, I want to take just mid of these. So what number should I select for the experiment?
I cannot give you an answer right now because I have not talked about instabilities yet. The main idea is that the number of ensemble members should be larger than the number of instabilities in the system. And I cannot quantify it because I haven't talked about what do you mean by instabilities. So once I talk about that, then maybe I can do this. And in fact, the correct statement is number of local instabilities. But for that, I need to first talk about instabilities and then local instabilities. And so there is a reasonable way to choose the ensemble size, but using ideas that I haven't yet discussed. So I'll come to that. Okay, so that's something that you can change. What else can you change? Sorry. I think that's pretty much all the parameters that I can think of, hyperparameters basically, right? And And then you can look at the various metrics. What is the error? Does the error decrease with time? Does the filter diverge? What is the precision? That is, what is the covariances? Do the covariances go to 0, some of them? Do they all go to 0? If all of them go to 0, that means the ensemble is becoming extremely precise, and almost surely it will fail and lead to filter divergence. So precision, accuracy, error, accuracy is related to error, of course, are all these things that you can then, as a diagnostics of how the filter is working. Yeah. Oh, the other parameter, of course, you can change is the inflation, and finally the localization, which I will talk about in the afternoon after lunch. Yeah. Localization will be after lunch. Yeah? Because I have to show the picture. And so instabilities in the remaining 25 minutes. That's a good time for talking about it. So, any questions about this? Matrices, I'm going to erase all the stuff about matrices and so on and so forth. I will do it in the language of differential equations. I hope that's okay. So, how many of you have never taken any differential equation course or have not solved any differential equation ever? For example, including something like a one-dimensional linear differential equation, linear homogeneous differential equation, which is this, x dot equal to ax or dx by d. By x dot, by x dot I will always mean dx by dt. Yeah. How many of you do not know what the solution is? If you don't know, that's perfectly okay. But I just need to know whether you know or not. If you don't, then please let me know. What is the solution? Sorry?
Ax square by 2 plus.
Nope. Not quite. You're not integrating x. So log x, not log. Well, there is a log x appearing somewhere. I want x as a function of time. Log x is in fact equal to, but can you invert it for me? Exponential. Anything? Any other choices? Log, which is the inverse of the exponential. Exponential. Okay. So it is e to the power at times x naught. Yeah? So at time t equal to 0, this is 1, it is x naught. So this is called the initial condition, and this is the solution. Yeah. So if A is positive, if A is negative, what happens? As t goes to infinity. If A is negative, then x goes to 0. If A is positive, x goes to infinity. If A is equal to 0, it is just constant. Yeah? That's the basis of stability, instability, and neutral. Neutral is stable. That's a term that is a bit uncertain, but anyway, right? So on the borderline between stability and instability, basically. Okay, so why do we say, and does it matter? By the way, nobody pointed out one thing, which is, does x go to infinity? Always? What about x naught is minus 17? If A is positive, x naught is minus 17. X, as t goes to infinity, what happens? It goes to negative, so I should have been more careful. It's sine of x naught. So it's plus minus infinity. It's either plus infinity depending on x naught is 0 or x naught is negative. And so one way to visualize this is as follows. If I'm looking at x, then either in the case when A is positive, if x naught is positive, so x naught was, let me put x naught here. So if x naught was here, the x of t will go to infinity. If x naught was negative, and this was 0, then it will go to negative infinity. And of course, if x naught equal to 0, then it will stay at 0, and that's called the fixed point. So x naught equal to 0 or x equal to 0 is called a fixed point in the sense that it doesn't move. If you start with x naught equal to 0, x of t equal to 0, you remain where you are, you never move as a function of time. Only when x naught is non-zero can you move. And which way do you move? Do you go farther away from the fixed point? Or in the case of a less than 0, what happens? When x naught is positive, it approaches 0 from the positive side. The x of t remains positive always, but goes to 0. And if x naught were negative, in the case when a is negative, then you will approach 0, but from the negative side, right? And so either you can stay where you are, fixed point, or in this case you can go away from the fixed point, and that's why it's unstable, or you can come closer and closer to the fixed point, and that is what is called stable. If I were to start with an ensemble of initial conditions, a whole bunch of initial conditions, I take 100 different initial conditions, randomly selected on the straight line, and A is negative, what will happen as t goes to infinity? So I start with many different x naughts, here, and so on and so forth. And I look at the solutions as a function of time, and look at for large times, as t goes to infinity, what will happen? All of them will come closer and closer to 0. So for example, think of this as the initial ensemble. It has a finite variance. It has a finite standard deviation. As time progresses, this will keep decreasing and becoming smaller and smaller and smaller. The covariance of the ensemble, the variance of the ensemble will decrease in time. Exactly the opposite way, which is start with a bunch of initial condition, all finite, so the variance is finite. The case when A is positive, what will happen to each of those solutions? Each of the solution is going to go farther and farther away from 0. The ensemble is going to become larger and larger and larger. The variance is going to become larger, and the variance will eventually go to infinity as t goes to infinity, right? So this is an example of where, so in this case, the variance of an ensemble will go to 0. In this case, the variance of an ensemble will go to infinity. And in this case, what will happen? So you start with a bunch of initial condition, you have a whole bunch of ensemble members, you have some finite variance. What will happen to the variance in this case? Sorry? Louder, I can't. Is one side coming to 0? If x naught is positive, it still stays there. If x naught is negative, it still stays at the same place. So each ensemble member will just stay where it is. It's not changing. So in this case, in fact, the sample covariance will be constant as well. Okay, so that's a trivial case. So this is, the borderline cases is something that usually never happen anyway in practice. So we'll not really discuss these kind of border cases, right? So it's either stable or unstable. Those are the two important things. Now what happens if it's more than 2 dimensions? Sorry, more than 1 dimension. This, we can draw a very nice picture in all of these cases. In this case, no? We can also draw a picture if I add just one more equation, which is so this is equation number 1. I'm now going to talk about 2-dimensional systems. And the second system happens to be dy by dt equal to by. Identical solutions, right? I mean, identical means the solution is basically very similar looking. Y of t equal to e to the power b t times y naught. And now this is happening in the vertical axis. Same story. If b is positive, this is unstable. If b is negative, this is stable. I want to put it all together by doing the following, which is that if I now draw the x and the y space together, I have an initial condition which is say x naught, y naught. And suppose we are in the case when both of them are negative, what will happen to such an initial condition? So x will decrease in time, right? E to the power at, a is negative, x is decreasing in time. B is negative, this will decrease in time, both of them decrease in time. They may decrease at slightly different rate, so they will not necessarily approach 0 at the same rate, but they will approach 0, maybe something like this. And same thing will happen to all the other cases. So right? And of course, if you start on the y-axis, you approach y and so on and so forth. And every arrow that I'm drawing is basically a trajectory. If you start with the initial condition here, you follow the arrow, and that gives you a solution of that system. And that's what these arrows basically mean in these cases. Yeah? So they will approach like that and so on and so forth. Yeah? So everything approaches 0. So this, by the way, y equal to 0 and x equal to 0, the origin is again a fixed point, because if you start with 0, 0, you stay at 0, 0. So this is a fixed point, and in this case, it's a stable or unstable fixed point. This is a stable fixed point, yeah, because everything is coming close to it. The exact opposite happens if B is positive and A is positive. Both of them are positive. Both the solutions x and y will go away from 0, and that will be the unstable case. All I need to do is literally flip the arrows. So if you flip the arrows, that literally is B negative and A negative. Okay, so I'm not going to draw it right now. Unstable case, fully unstable. Now, the interesting would be, of course, as you can imagine, when A is positive, let's say, and B is negative, what will happen in that case? I need a new picture for that. So I start somewhere here. A is positive, B is negative. What happens to the x component? What did I say? Let me write it down, otherwise I'll forget as well. A is positive and B is negative. What happens in that case?
Did you all take a course in differential equation? Ordinary differential equation analysis of equilibrium. That's what makes it.
Wait, okay, so all of you have gone through education, yourself, I hope, and the answer is yes or no. So I need a two-state answer and not a confused answer. How many of you have taken a differential equation course? Raise your hands. Please, please. Okay. How many of you have not taken a differential equation course? Wait, there is still, I think, a couple of people who neither said yes or no, or maybe their hands were like this and I didn't see it. Okay, so minority, but all of you are done. Okay, have you done the differential equation course where you studied stability of a differential? How many of you studied stability of a differential equation in that course? Can you raise your hands? Much smaller fraction. That's what I expect. Usually the OD course is matrix equation, one second order first. Yeah, I guess, how many of you have done nth order linear differential equation? Okay, how about, let's start with second order linear differential equation. Second order, most people have done it. Newton's laws, no? So, how about nth order, n being an arbitrary integer? So third order, fourth order, fifth order, different linear differential equations. How many of you have done that? One much smaller number. Okay. Yeah, so it's a mixed bag. Yeah. I guess
given a third order equation, you should be able to express a third order equation as a first order equation in a vector of size 3. Converting a third order equation to a vector of size 3, that's called converting it into a state space form. How many of you have done that? When he says that dots with an effect, so that's smaller. He's talking about the state space form, but a potentially third differential equation.
most courses that deal with yeah, most of the time they won't do it. That's quite common. So
if there is a gap in catching him on the fly, that may be different.
okay. So yeah, because I guess yeah, that's another aspect, which is that many of them may have done the second order, third order, and usually second order because that's Newton's laws. So that's quite common. But okay, A positive, B negative. What happens? What happens to the x component? X component will, as a function of time, will it increase or decrease? It will increase. What happens to the y component? That will decrease. So y component is going to come down, x component is going to go up. So it looks like this. In negative time, as time becomes negative and larger negative, exactly the opposite thing happens. So the trajectory will look like this. So this was the initial condition, and it's going to go like that. And I now just draw the arrows, convince yourself that what I'm doing is correct, which is that the other initial conditions will look like that. Eventually they will go like this, and then, of course, what will happen if you're, I shouldn't have these arrows, I don't need those. What will happen if you're on the x-axis? So x is equal, sorry, y-axis. X is equal to 0, y is non-zero. X will not change anyway, and y will decrease. So it is like this, negative, it will be like this. If you're on the x-axis, y is equal to 0, x is non-zero, this will remain 0, A will push you towards infinity or negative infinity, and yeah, so now this is mixed. The fixed point, which was at this point, if you take initial conditions nearby, one component decreases, the other component increases. So this is neither stable or unstable. Okay, that does not exist. By definition of stability, if solutions go away in distance, not in terms of components, then it's called an unstable fixed point. So if I'm starting somewhere nearby, the x component will decrease, so I'll come closer and closer. But what happens to the y component? It goes away, so I'm going to go away, which means I'm going away from this point anyway. So as a distance from the origin, the distance is going to continue to increase. Even though one component is decreasing, because one of the components is increasing, the overall distance will keep increasing, and hence this is also called unstable. Right? So there is nothing called a mixed stability. Okay, you can design, but okay. As a mathematical definition, A system is either stable or unstable, and this is unstable. There are, as I said, neutral stability and so on can be discussed, but yeah. Okay, so relating this to, again, back to ensembles. If we start with a ensemble like this, a set of initial conditions in a big circle over there, what will happen to those set of initial conditions? So this has a finite covariance, right? I'm just starting with some nice Gaussian ensemble. What will happen to these initial conditions as a function of time? All of them will do the same behavior as I showed for each one of these. The x component will decrease to 0, the y component will go off to infinity. Eventually, this will become a flattened pancake like this. The x will be very close to 0, the y component will keep increasing. It will keep increasing, but at a slightly different rate, and then it will just keep moving like this, right? Partly what we were saying in some sense, some eigenvalues were going to 0, and some of the eigenvalues were remaining finite. In this case now there is no assimilation per se. I'm just plotting what happens to the whole ensemble. When you do assimilation, what happens? So okay, that's a slightly different story. I think that needs a bit more thought. But this is the basis of where the dynamical instabilities play an important role along with the uncertainties. So if you think of the width of this ellipse as an uncertainty, right? That's exactly what it is. The width of the ellipse, which is the eigenvector, the eigenvalue in certain directions, that is the uncertainty associated to that covariance matrix. That uncertainty is being affected by the dynamics. In the stable direction, the uncertainty goes to 0. In the unstable direction, the uncertainty increases. And this is the basis, right? So this is the crucial aspect of how the ENKF actually also works in practice. The unstable directions will lead you to smaller and smaller uncertainties. Sorry, the stable directions will lead you to smaller and smaller uncertainties. The unstable directions will lead to larger and larger uncertainties. The observations need to control the growth of uncertainty in these unstable directions. Because if you don't control the growth of uncertainty, like in this case, there's no assimilation as such, I'm just solving a differential equation. As time t goes to infinity, this will keep going, and this will keep increasing and increasing and increasing, and I will have extremely uncertain system. By doing assimilation, what we are trying to do is to keep in control the uncertainty even in the unstable directions. The stable direction take care of themselves. The uncertainty in stable direction will decrease all by itself by the dynamics. The uncertainty in the unstable direction will keep increasing unless the observational information is used in the assimilation in order to keep reducing the uncertainty. And that is not straightforward to explain. Sorry? Right now?
I don't know. Not now.
Lunch? Afterwards? You have given me like 15 things to finish in the afternoon. What I will do is I will make a priority ordered list of things I should talk about, and I'll need your help to make that order. So let's discuss it, and then we can decide which one to.
How to compute the changing area?
Yeah, that will be useful. That will be very useful. Okay, so just one quick food for thought before you actually go to eat food. So you can see that the solution to the differential equation is a function of time. Of course, that's what is meant by solving a differential equation. You want to find the solution, the x as a function of time, y as a function of time. That's the solution to a differential equation. It also clearly depends on the initial condition. If the initial condition changes, of course, the function changes. So this is a function of the initial condition and the time. So if I were to write down, now I'm making a big jump, which is so n quantities. This was from the Lawrence 96. It's a 100-dimensional dynamical system. It's n is 100, so there are 100 differential equations. Lawrence 63 has 3 differential equations, n is equal to 3, and so on and so forth. So I'm writing it compactly like this, but effectively think of x and y as 2 components of a 2-dimensional vector, and so on and so forth. Yeah? So conceptually, it's not that different. Mathematically, things become slightly more difficult. Okay, so the solution is a function of time, but of course also a function of the initial condition So I choose a point in the n-dimensional space. That's the initial condition. We are choosing it randomly, for example, in the code. And the solution will depend on, of course, the time, but also the initial condition itself. What do you mean by, so if I have a x naught somewhere here, and if I have a x naught tilde somewhere there, the trajectory to this may go like that, the solution to that equation, and the solution to this x naught tilde may go like this. Right? What happens to the difference between these two is exactly what is meant by sensitivity to the initial condition. And how do you understand the dependence of a function on one of its variables? Of course, the derivative. So the matrix M, which is the derivative of x with respect to the initial condition, rather than derivative with respect to time. The derivative with respect to time is f of x. The derivative with respect to now the initial condition basically gives you the sensitivity with respect to initial condition. Right? If you change the initial condition by a small amount, what's the definition of this? It's x, x of the solution x minus the solution x with x naught tilde as x naught and x naught tilde become closer and closer and closer, right? So this is a n cross n matrix. Why is it n cross n? X is n-dimensional, x naught is n-dimensional. This is a multi. So if you have not done multivariable calculus, this is going to be tough to explain. But hopefully you have done at least some multivariable calculus. And so this is a derivative of a n-dimensional vector with respect to n-dimensional vector. And so that's a matrix, and that's called Jacobian. So this is the Jacobian of the solution with respect to initial condition. There is a corresponding one that is for the Jacobian for f. Of course, there is a Jacobian for f, which is, so capital F of x, which is equal to del f by del x. That's a different one. Yeah, and those two are related. Eventually, we'll come to that. But this is the matrix of interest, and we can write down, in fact, the differential equation for this matrix, or the difference equation, which is what Varun was talking about. And that gives you how these evolve in time. In fact, that also tells you how the uncertainties evolve in time, because the uncertainties are nothing but how these kind of arrows, the difference between these two, will evolve in time, and that's like evolution of uncertainties. So the evolution of uncertainty is also related to the evolution of these matrices. And yeah. Okay. In order to generate an initial ensemble, the main restrictions would be for a real dynamical model, would be related not specifically to whether you get, so there is nothing like a right distribution to follow. As we saw, basically an initial prior ensemble is a arbitrary choice. If the system, if the data assimilation system, if the filter is stable, which it should be, if it's not, then you anyway should not be dealing with that filter. You should devise a system where the filter is stable. And if the filter is stable, then the initial distribution will not matter too much. So you essentially want to get sufficient variability in some sense, but not exactly how you get it is not that crucial. Now, what is important is, of course, that your model shouldn't blow up. And that's so if you're solving a partial differential equation, and let's say you have some, so the simplest method, say finite difference method, and your state happens to be, so your variables in a finite, in a PD solution. So suppose I'm solving a one-dimensional partial differential equation, and the domain is 0 to 1, and I have some grid points, and the function I'm trying to represent is simply cosine of 2 pi x. So no, well, what is this? 2 pi something. Anyway, pi x. Anyway, so this is the function I want to represent, and this is my initial condition, and I want to perturb it. Suppose I perturb it by adding random numbers, and the random numbers give me something like this. Right? So my initial condition may look like that, right? That will be a terrible initial condition for a typical PDE solver. You will just have very high derivatives unnecessarily in your initial condition, and that will just lead to instabilities in the solver itself. You completely want to avoid that, for sure. Another example is, classic example is balance. If you randomly perturb initial conditions, that may disturb balances that are crucial for a valid atmospheric oceanic state. For example, something like hot water at the bottom of the ocean and cold water at the top of the ocean. Okay, I'm just exaggerating, but basically that's the idea of the balance, right? And so something like that kind of initial condition is not a good idea to use. So actually, to generate initial conditions in practice, one of the things would be run the model for some time and just pick the solutions of the model at different time instances to give you a variability. That's one way to do this. How do you generate initial conditions in order to maintain balance? I don't really know. I've never done it in practice. No idea. I only know the theory behind it, and that's all. So nothing else. Yeah.
Okay, sir. Thank you.
Yeah. Okay. Somebody will answer this question next week, maybe? Yeah. Probably. That's my guess. I hope.
Next week, these questions will be answered.
Yeah, exactly. So I think all the practical questions, keep it for next week.
Right.
Okay,
Don't ask me. I'll give you wrong answers. So.
Yeah.
Never done this in theory. So, sorry, I mean, never done this in practice. Sorry?
There is no wrong in the research. We will learn from that.
Okay, we can discuss that later. Fine. Anyway, so just hold on 1 second. Something is happening. I don't know what. I don't see everything on the screen. Something is. I think this is the shared screen with that. You can see that. Share. Yeah, I have shared my screen. No? That's why you are seeing this. This is my screen. But I can't see the full, so something, anyway, it's okay. It's not that crucial. I think maybe I can, I mean, basically I don't need all this. Oh wait, I don't need, I just want to minimize this thing, that's all. Anyway, it's okay, fine. Okay, right now at least there is nothing missing. Oh, okay, good, they fixed it. Perfect, thank you. So, sampling. So, the point, there was homework given to me by Varahan, which I need to finish, which is to talk about the modularity of that code and how, if you start from scratch, how do you build, say, Kalman filter, ensemble Kalman filter. Localization, I haven't talked about, which I want to do. And the ensemble transform Kalman filter, which is practically one of the most useful filters around. And then the local ensemble transform Kalman filter, but I'm not going to talk about the local ensemble. So I'll talk about localization and ETKF. I think in that order is probably better. So here we go. So what's the idea behind localization? Suppose you have the true covariance. This is from the book, the reference for which I will put up. Let's say there are 100, whatever, 300 variables or 200 variables, 0 to 200. And the covariance matrix, the true covariance matrix, happens to be as shown here. So basically, the variables that are nearby have high correlation, dark colors. The variables which are farther apart have small correlations. Those are small light colors, right? I don't know why they are all positively correlated with no negative correlation for some reason. Anyway, that's the example that they chose. This goes between -1 to 1, the correlation here. Okay, so the dark colors are the high correlation, the light colors are the low correlations, small or zero correlations. And we want to represent this using a sample. So you sample, and this is actually just Gaussian distribution. There's nothing fancy. The distributions are simple, except that they have a structure such that points which are nearby, variables which are labeled nearby, have high correlation. The variables which are labeled far apart are low correlation, and that's a true correlation matrix. If you take a finite sample, in this case they chose, I think 20 or something like that, I forgot, it's in the caption of the, 20-member ensemble. So with a 20-member ensemble, the covariance matrix, the sample covariance happens to be what is shown over here. Now, if you see that, now suddenly you get these dark colors on the other sides, right? And also the very light colors which are negative correlations. So you develop, because the ensemble covariance is an approximation, the approximation results in one part, which is that the points which are far apart are also highly correlated, positively or negatively highly correlated. You don't want this to happen. What do? Well, if you happen to know that points which are far apart are going to be, or you want them to be not highly correlated, you suppress it by fiat. That is, you set them equal to 0, for example. So you can simply go ahead, look at the diagonal elements and everything that's off diagonal, sufficiently far away from diagonal, let's say 4 or 5 or 6 off diagonal elements, beyond the 5 or 6 diagonals, you set it to 0. And everything in between, you keep it as it is. Okay, that's not such a good choice, because then you're not, suddenly everything, you will have sharp boundaries of 0 and non-zero. So you taper it. So things that are close to the right diagonal, they are suppressed by smaller values. Things that are very far away, that are suppressed by large values, and that is what is done, and that is what is called localization. So you basically take you look at the sample covariance, right? The sample covariance PF has this structure which has, so index 1 to up to 200 and index 1 to up to 200. That's what it's, the indices are shown like that. And so in that matrix, look at, let's say, the index phi and index 200. So this entry here, phi and 200 will be here, index phi and index 200, and just multiply it by a function which depends on the difference between the two. So if this is I and this is j, then you multiply it by a function of I minus j, such that when I minus j is large, this function should be 0. When I minus j is small, that function is close to being 1. And effectively, the function of I minus j that you choose looks something like this. So at near 0, it is equal to 1, or at 0, it is equal to 1. As you go farther away, it goes to 0, and it's chosen in such a way that, in fact, it just goes to 0 after a certain limit, and this is some number c. And whatever choice of the function that you want to choose, there are multiple choices. There is a very commonly used function that is also shown in the book here. So here is the function. Oops, where is it? Oh, sorry, I'm going the wrong way in the file. It's this function. So this is the specific Gasperi cone. I think this is not the same cone, I don't remember now, as the one I referred to yesterday. And this is a fifth order polynomial, piecewise fifth order polynomial that's patched together in order to get something that looks kind of like a Gaussian distribution, except that it actually goes to 0 after a certain limit. And that limit, that number can be changed. So the polynomial looks like this. The exact form is not that important for us to know, but basically the idea is that this function, if you plot it, it looks like the one I showed there, right? And so you simply multiply the entries of the covariance matrix by these values, by the function R is I minus J, the index. Okay, so that's if you have the indices I and J. How do you use it in practice? If you expect the correlation between certain variables, for example, temperatures that are, say, beyond 100 to 200 kilometers should not be correlated, or say humidity, different variables could have different ranges that you expect the correlations to be 0 or non-zero. So for each of those variables, you apply a function of this form such that the correlation values of, say, the temperature between here and New York should be set to 0. The correlation of the temperature variable between here and New York should be set to 0. Between here and Pune should be suppressed by value that's somewhere in between 0 and 1, and so on and so forth. That is given by some function along these lines, and this is quite a commonly used function. Right? And so this is what is called localization, because you're essentially keeping local covariances to be non-zero, and that things that are away from being local are set to 0 by hand. So the covariance elements of the covariance matrix are set to either 0 or non-zero, or are multiplied by a number that's between 0 and 1 based on the distance, physical distance in the real space on the earth being used. So R is essentially, in the artificial example, I and J essentially are the locations on the earth, for example, right? R will be literally the distance between the two locations. And C is some factor that will take care of what do you mean by R going, it has to be scaled by a factor that depends on the variable of interest. So that is, and so this is element-wise multiplication. For every element in the matrix, you figure out, so if the 5th element and the 10th element is the humidity in New York and the 10th element is temperature in Pune, then you try to figure out whether you expect the correlation to be 0 or not, and then you set it to multiplied by appropriate factor that is given over there, right? Depending on the distance between New York and Pune. With this kind of form, of course, this will turn out to go to 0 exactly. And that is what is called localization. In the case of the Lorentz 96 models that we were discussing in the morning, x0, x1, x2, and so on and so forth, it's basically just the index. So the index x1 minus, x1 minus x7, it's the distance r is basically 1 minus 7. Absolute value of 1 minus 7, so 6, and so on and so forth. And then the C there sets a scale. How many grid points do you want to call 0, and how many grid points do you want to set to non-zero? And if I go back to the notebook, which I had earlier, oh, actually, I opened too many things. Okay, so here, oh, this is L63, L96. So what I didn't show in the morning was this is the form of that polynomial. It's a 5th order polynomial. And if you plot it, it looks something like this. So it goes between 0 and 1. Near the diagonal, it's 0. Sorry, it's 1. Off the diagonal, it's close to 0, and then it tapers off smoothly. And this was being used in the L96 code in the morning. I didn't explain what was being done. And how do you actually use this row? It's element-wise multiplication. It's not matrix multiplication. For every element of the covariance matrix, you multiply this. Or because we don't really want to use the covariance matrices per se, we really just want to use the ensemble matrices, you can multiply it to the ensemble. So the way it was being done is, if you see, oh, sorry about it. In this simple code where I was using the first form of the equation of the Kalman gain, it was really just multiplying the covariance matrix itself. You don't need to do this. Remember the homework that I gave you, which is write down the code for the last line that is more computationally efficient. last line on the board that was there in the morning, now it is not there. And in that form, where do you apply this form of correlation? Oh, sorry, this form of localization? Well, you apply it to the Z matrix effectively. Yeah? So before you compute the H, Z, and so on and so forth, the Z matrix itself should be localized so that the correlations coming from that Z matrix turn out to be 0 for variables that are far away, and only the variables that are nearby have finite correlation. Yeah. So, so maybe one option is the following: make for a few of these time steps, plot the covariance without the localization, and then also plot the covariance after applying the localization, which is multiplication by rho. So the star is element-wise multiplication in Python. At is the actual matrix multiplication. So this is not in the notebook, but it should be straightforward. You plot this object, you also plot it after multiplying by the localization and see what the structure looks like. And the picture will be somewhat similar to what I showed from that book. And I'll put the reference for the book and the section number and so on. Okay? Okay, so that's localization. That is essential because otherwise, because of a small sample size, the correlation which you expect to be non-zero turn out to be, you expect to be 0, turn out to be non-zero. This is kind of like a count, it goes against what we were talking, not against. It goes in a different direction to what we were discussing in the morning. In the morning, we were discussing inflation, which is you want to inflate the correlations, right? We were saying that the ensemble becomes too sure of itself, the variances become too small, hence you want to inflate. Localization is trying to set to 0 elements of the correlation matrix which you expect to be 0 and which happen to be non-zero because of small ensemble size. You see that these two are exactly the opposite in some sense. This is structured. The structure is given by your physical understanding of the system. That is, if you expect in physical space something to be the correlation between variables at physically diverse location to be 0, you set them to 0. Inflation was this mathematical understanding of why the ensemble is collapsing and becoming very, very small variances. You want them to inflate. Now, okay, so those two look like kind of opposite tendencies. So unfortunately, both of them have to be used. You have to apply inflation, and at the same time, you want to apply localization. Why? I don't know. There is basically no theoretical basis for inflation or localization. It's purely ad hoc, practical hack in order to get the ensemble Kalman filter to work. And that's pretty much where it stops right now. There is some, okay, there's a little bit of theoretical understanding of localization, one paper, literally one paper, but anyway, so it remains at a very, very unsatisfactory level in terms of theoretical basis of this filter. Okay, so localization, that was one thing. The other, remember the main rationale behind inflation was that if you do not have inflation, we had a missing factor in the covariance calculation. So we wanted, the Kalman equation looks like this. Oh, this is PA, right? Without the observation perturbations, without adding the UIs, the observation perturbation that we discussed in the morning, the ensemble looked like something like this times exactly the identical term multiplied by I minus KH transpose, and this was an underestimate of this object as we discussed in the morning. And so we don't want to do this. And hence we added the UIs. The UIs afforded us this, and then everything was good because this happens to be equal to that. And that's how it worked out, right? Suppose we don't want to deal with these stochastic perturbations, but we want to achieve this, then what do? We cook up a transformation such that this can be achieved. So the methodology or the philosophy is as follows. You devise a transformation between the forecast ensemble and the analysis ensemble by some matrix X such that, so the method is that find X such that if you set this to be the case, then ZA transpose, which is equal to basically the P hat A, happens to turn out to be equal to I minus KH P hat F. So we want to find a X such that this is true, right? That's the main goal behind what is called, or what are called in general, square root filters. Why square roots? Look at this equation. This is a covariance matrix. This is Z times Z transpose. That is what is called a matrix square root. So for a matrix, you can't just take a square root. That doesn't make sense. So matrix square root, this is the definition of a matrix square root. A matrix that satisfies this identity, that and this can be done for positive. So let's stick to symmetric positive semi-definite matrices for now. Others will forget about those. So this is a positive semi-definite symmetric matrix. And for such a matrix, a split of this matrix into this form, ZA times something times its own transpose, is called a square root. So this is a square root. ZF is a square root of P hat F, and so on and so forth. And so now we are just dealing with square roots of the matrices. So that's why these are called square root filters. And deterministic because this transformation does not involve, as we will see in a minute, the X turns out to be a deterministic matrix. That is, it does not involve random number sampling at all. The UIs that we added to get this term included random numbers. The UIs were random variables. The X will turn out to be non-random and deterministic, and hence these are called deterministic square root filters. And here is a method to get to the deterministic square root filter. Or one way to motivate, either I can write down the ansatz and then show that this is true, or let's just go through the motivation. Yeah, okay. So where do we start? We want this to be the case, and except that, oh yeah, we want this to be the case, right? And we have expressions for all of these objects that we had written down in the morning. So they are all gone now. And so I'll start from here and try to find X. That's a methodology. Yeah. Okay. So let's start writing down what PF for. P hat is ZF transpose. K was written in terms of, so let me write down that form of K again. Remember K was, by the end of a data assimilation class, the expression for K should be drilled into as much drilled into your mind as, for example, what's the solution of ax square plus bx plus c equal to 0? That you can, if I shake you in the middle of the night, you will just write, minus b plus minus square root of. So just like the quadratic equation is drilled into your mind by your school teachers, the Kalman gain and the expression for these should be drilled into your mind, because these are so fundamental in most of the modern filters. Okay, so what's K? PH transpose times HPH transpose plus R inverse. And that I wrote as, so P was Z, so this was ZF times HZF transpose, and then again the same thing, HZF and HZF transpose plus R inverse. Yeah? That was the expression. And I said we will only deal with these matrices and not deal with the full covariance matrix at all. That was the main aim. And that's where we will go now. So we want to write down the split up. So let me just go ahead and look up what's the easiest way to write this split, which is in terms of the matrices. Okay. Now I see. So once I substitute this K in here, and PF happens to be equal to ZF transpose, put it all together, and we will see that this expression I minus KH PF hat is equal to, I will now start writing I times PF, which is ZF transpose minus KH PF. K is over here, so that is ZF. That's on the left, which is the same factor here. This matrix will be indicated by V. So HZF, let me get this right. HZF transpose is V, yes. So if this is V, we have the K, which has basically V times all of this, which is, did I get this right? Oh, actually, all of this will be written as D inverse. Yeah, so this whole big inverse will be D inverse.
The same D that we used in calculus.
Yeah, so the symbols are consistent, which is amazing. I don't know how that happened, but never. And then there is a H times PF. What is PF? This is ZF transpose. So H times ZF will be V transpose, and then the remaining factor will be ZF transpose. Okay, if you're not convinced of this, maybe another one-line algebra in between, right? So what do we see here? There is this on the left, there is this on the left, there is that on the right, there is that on the right. They will come out on the left and right, both sides. And what I will get is ZF times identity minus, this has gone, that is gone, V D inverse V transpose ZF transpose on the left and right. Yeah. And now I want to try to deal with this object, which is where the Sherman-Morrison-Woodbury formula comes in. Okay. So that's the non-trivial step basically. The rest follows by straightforward algebra. So the only non-trivial step is the Sherman-Morrison-Woodbury formula. So this happens to be equal to, and I will not prove it, and this is by the Sherman-Morrison-Woodbury, happens to be equal to I plus V R inverse V transpose inverse. So this is not an inverse of any matrix, it's I minus something. I've converted that into inverse of something. Inverse of what? I plus V R inverse V transpose inverse. Why is that a good thing? I mean, inverses typically are bad to deal with. But the reason why this may not be such a bad idea is because the dimension of these matrices now. So that's where the ensemble space comes in. What's the dimension of V? It's H times ZF transpose. So this is, remember H was M cross N. This is N cross P. P is the dimension of the ensemble or the size of the ensemble. So this is M cross P. Right? And then, V is the transpose of HZF transpose, so it's P cross M. P is the dimension, or P is the size of the ensemble. M is the number of observations. So this matrix is P cross P. Basically, this lives in the ensemble space, not in the model space, not in the observation space, but in the ensemble space. The ensemble space, which is spanned by the ensemble, which is typically small dimensional. And the inverse of this matrix is not then such a bad idea. So even though there is an inverse, it's okay to deal with it. And this basically gives you an idea of what to do, because this is what we want. There is already a ZF, there is a ZF transpose. Remember, we want ZF times X times ZF transpose. sorry, X transpose times ZF transpose. The ZF is here, the ZF transpose is here. So essentially the square root of this should be the X. And that is what is done in the ETKF. So ETKF, the ensemble transform Kalman filter, is using the square root of this matrix as X. So X is basically a square root of I plus V D inverse V transpose inverse. Yeah. To be precise, basically this is done through, I mean, the easiest way to do this is through eigenvalue decomposition and so on and so forth, but I will not go through that detail. So you, just to be sure, so basically you write V D inverse V transpose, the eigenvalue decomposition of this symmetric matrix, which is in the ensemble space. So this matrix is just, suppose you have the ensemble size is 100, this is just a 100 cross 100 matrix. Eigenvalue decomposition of a 100 cross 100 matrix is very simple to do, and that's nothing complicated. And that, suppose you write it as C gamma C transpose. This is the eigenvalue decomposition of this matrix. And then I will leave it as exercise to check that X happens to be, if you choose X to be equal to what? C times identity plus gamma to the minus a half, it does the job that we set out to do. That is, this is the square root that we will use in order to get the ensemble analysis covariance to be equal to I minus KH times the ensemble forecast covariance. And this choice of X, this choice of the square root of this matrix, achieves that objective. So this is another couple of lines of calculation that you can do then. Yeah. Okay. So that is what is called the ETKF, the ensemble transform Kalman filter. The local ensemble transform Kalman filter is simply kind of combining the ideas of localization and the ETKF. What was the idea behind localization? The observations, or rather the variables that are far apart, are not correlated, so you should not be really dealing with long-range correlations. The idea behind local ensemble transform Kalman filter is that, well, if the variables, in the sense that you are trying to, say, find correlation between something here and something in Nagpur, shouldn't be correlated, but even the observation should have the same behavior. That is, the observation remember the observations are local in time. We are always assuming that the state being observed is at the current time. The observation that we get is of the state at that given time. Now, if the observations are local in time, then the observation somewhere far away should not affect the state here. There should not be a correlation between the observation somewhere else and the state somewhere else, if they are far apart. So the idea behind local ensemble transform Kalman filter is to use the ETKF, but only by keeping observations which are local in region. So if I want to update the state in Bangalore, I keep observations only in a 500 kilometer, 200 kilometer radius in Bangalore, maybe by applying the Gasper-Cohen correlation tapering. And everything else, all the outside observations are thrown away, and then you apply this ETKF locally at each grid point, each point in the physical space. And that's a local ensemble transform Kalman filter. How to actually implement it is kind of complicated, of course, but so I'll not discuss the actual implementation of LETKF, but that is what is called a local ensemble transform Kalman filter. Okay. Question? Yeah, sure. Of course.
There's a square root version. This is an ensemble square root version. You can read it in the Kalman filter in the square root version. This is the ensemble version of the Kalman filter, ensemble version of the square root filter.
Yeah. So basically, where is the, so one, I guess essentially the comment is that for any, see, I said that ZF is the matrix obtained by having columns which are the ensemble members and the mean has been subtracted. That is actually not necessary at all. As long as ZF has the property that ZF times ZF transpose is PF, any matrix of that form is okay, yeah? So any square root actually will satisfy this equation and you can work with any square root. It doesn't need to be ensemble, it doesn't need to be related to the ensemble. So, but the Slack channel and posted this 4-page extremely nice review of square root for ensemble square root. No, what is it called? I forget the title of the paper. Basically, it talks about square root filters and then talks about ETKF, the ensemble transform Kalman filter. Oh, wow. What is this? Okay. I think I can. So I will switch to the slides now so that this thing doesn't happen. And okay, so. Sorry, can we have personal conversations outside the class? Thank you. Okay, so we talked about the sampling, all the ensemble filters, ensemble Kalman filter, ETKF, ensemble transform Kalman filter, and particle filter, which I didn't talk about, are based on the idea of sampling, and we discussed this a little bit. So let me sort of say do the last bit of it, which will take you towards the particle filter, and that involves. So remember the idea behind sampling, that you have a density f of x that you want to try to understand something about, and x1 through xn, the samples, the ensemble that you have are representative or basically identically distributed independent random variables that follow the same density f of x, right? And then the sample mean happens to be a unbiased estimator. The variance can be reduced either by increasing the sample size or by decreasing the variance of the function that you want to compute, right? This is what we were. So this is where I stopped essentially, right? The error decreases with either increasing n or decreasing the variance of the function. Okay, so that's one option. The other idea is importance sampling. So let me introduce importance sampling, which is the crucial theoretical bit behind particle filters. I realize that change of measure is not a very useful terminology, but anyway, sleight of hand is probably better. So here's the sleight of hand, which is if you want to compute the expected value of a function g with respect to the density f. So remember, we were always discussing the sampling in terms of computing expected values. The histogram is basically expected values of a bunch of indicator functions which are 0 outside a certain interval and 1 inside a certain interval, right? And so on and so forth. So sampling is very closely related to computing expected values of functions. So if you want to compute the expected value of g of x as with respect to the density f, the definition is clearly this: integral of g of x f of x dx. That's the definition of the expected value. Okay, are you happy with this definition in the first place? The expected value of the function g with respect to the density f is written over here. Most commonly, the probability densities are written as p of x. So if that's comfortable for you, think of f of x as p of x, but actually don't, because I'm going to introduce p of x in a minute as a different function. So, okay, so this is the expected value with respect to f of x. Now the sleight of hand is simply that if p of x is a probability density such that it's non-zero, for example, the Gaussian density, it's never zero anywhere, and so on and so forth, then I can simply divide and multiply by p of x, That's the sleight of hand, right? Most mathematical tricks involve multiplying by 1, which is what I've done, p of x divided by p of x, or they involve adding a 0, which is a quantity minus the same quantity. Anyway, so this is multiplication by 1. And now, basically, what does this look like? If p of x is a probability density itself, then this expression in the second place is the expected value of the function gf by p, right, with respect to the probability density p of x. So now instead of computing the probability density with respect to f of x, I'm computing the expectations with respect to the probability density p of x, but of a different function. What is the different function? The different function is f times g divided by p. Maybe I should have written it slightly differently, which is slightly better way to write it, which is the original function that we wanted to find the expected value was g times f divided by p. That's what in the parenthesis on the last is the function which is g times f by p. F is the original density of interest. P is the new probability density that I concocted for no good reason. And this is the ratio of f by p, the density of interest divided by the new density. And this new density, the p of x, is what is called, unfortunately it's not on the slides. This is the p of x is what is called a proposal or a importance sampling density. So the ratio of f by p multiplied by g, the original function, is now the quantity of interest that we want to evaluate, or whose expected value we want to evaluate. Of course, when we want to evaluate expected value, we would like to understand what the variance, that is, what is the error in some sense, or how much is the, okay. So this computation is straightforward. I will not go through the steps, but the variance of this g bar, now the new function that I'm calling g bar, the g times f by p, the variance of that quantity happens to be equal to, actually it's straightforward, right? This is basically the definition of the variance. How do you define the variance? The quantity squared minus the expected value of the square minus the square of the expected value. That's the variance. This is exactly the definition of the variance, basically. Yeah? Okay, so the last quantity of interest, the last quantity in this equation is simply the square of the quantity of interest. It is exactly this expected value of g with respect to f, which is also the expected value of g bar with respect to p square. So we can't really do much. By changing p, we cannot change this quantity much, because that's the expected value, which is what we want, and so on and so forth. So we can play around with this in order to minimize the variance. So how do we minimize the first term in the variance? Because we want the estimator to have as small a variance as possible. One way to minimize the variance would clearly be, if p of x is proportional to g times f, then that will minimize the variance. Okay, so this is maybe a 2-line computation. I don't know, 5-line, depending on how fast you do computations. I'm not going to go through it, but this is part of the homework, that verify that the choice, so p of x is what we want to invent in order to minimize the variance. So effectively, you want to minimize this quantity written over here as a function of p of x, right? For what choice of p of x will this object be a minimum? And that turns out to be simply proportional to g times f. We don't know the normalization. Remember, we want the p of x to be a normal probability density. If we want it to be a probability density, it needs to be normalized. In order to normalize this, what is the normalization constant? Oh, what's the normalization condition? Integral p of x dx equal to 1. Integral g of x times f of x times the normalization constant dx should be equal to 1. How do you evaluate this? To evaluate this, you really need to evaluate the original integral. Okay, so that's a bad choice. The normalization constant is the original integral that we are trying to evaluate. We are going around and round and round in circles, right? We cannot normalize this, or rather we cannot normalize in the sense that in order to normalize this density, we really need to evaluate this integral, which is what we wanted to do in the first place. So this is not a terribly great choice. The intuition behind this is actually though useful, which is that P of x should be close to the product of G and F. So here is so to say a picture that I can draw, and so let's say f of x was some density that looked like this. So this was the density f of x, right? And I want to evaluate the integral that is expected value of g of x, where g, and this is something that, right? So it's going to 0 beyond this point, and g of x happens to be a function that is non-zero in this region, but it's 0 everywhere else. Yeah, so this is g of x. Yeah, what will happen? When you just take the product of these two, basically most of the places the product will just turn out to be 0, right? Here is 0 because g of x is 0. Here f of x is close to 0, so the product is close to 0. And so when you want to evaluate such kind of integrals, what's the right choice of p of x? The intuition here says that the p of x should be such that it is close to the product of g times f. G is exactly 0 outside this interval, suppose, for the sake of this argument, so that I can get home a point. So then the product is going to be 0 outside and a small value in between here. That's what it is. But you want to normalize it. So effectively, suppose I choose a Gaussian distribution such that its support is somewhere here, but it goes to 0 outside that, right? So it tapers to 0. It's Gaussian. Why Gaussian? Because Gaussian is easy to sample from, for example. Or I could use a uniform distribution in this region or something along these lines, right? I'm taking an artificial example clearly, right? G of x is not, you would never want to evaluate expected value of function like this, but this is artificial. But the point is that you choose the proposal in such a way that it's near the point where g of x, or it's non-zero wherever g of x and f of x are significantly non-zero, and it could be small everywhere else, and that is perfectly okay. So that's the intuition that basically comes out by this mathematical calculation, that the variance is minimized when p of x is proportional to g times f. We cannot compute the normalization constant, but the intuition says that choose a normalized distribution such that it is non-zero wherever g times f is non-zero, and otherwise it could be 0, and that's okay. And so that's basically the main idea behind what is called importance sampling. So the idea is now, instead of sampling out of f of x, remember in the original problem of sampling, we said x1 through xn are random numbers which have the same density, are random variables, such that they're independent, identically distributed with a density f of x. The problem now gets shifted to, instead of sampling from f of x, sample points out of p of x. So, by the way, the other reason for doing all of this stuff is f of x, something like this form, is usually very difficult to sample from. Gaussian random variables are easy to sample from. Uniform random variables, easy to sample. And there are a few other well-known random variables that for which you can simply write a one-line Python code and sample. That's not the reason. Computationally, they're efficient as well, but and so on, right? So we want to choose typically the p of x such that it's easy to sample and it's close to non-zero, where f of x times g of x is non-zero. And that's the, yeah, okay. So the same computation that we did for variance and so on and so forth applies to this new object. That is, now instead of taking a sample from f of x, you choose the new sample. Maybe I could have used a different symbol, y1 through yn, but anyway, sorry, it's x1 through xn still. x1 through xn is a sample from p of x, not from f of x. But in order to get a correct estimate of g, of the integral of the expected value of g, sorry, correct estimate of not g of x, expected value of g of x, we need to define a weighted mean, because remember that factor f divided by g that appeared. Sorry. The wn here should be f divided by p, not f divided by g. Oh, that factor is gone. I erased it. The g bar, the new function that I defined, was g multiplied by f divided by p. That's what should appear here. So this should have been p of x of n, not g. I'll make that correction before I upload the slides. So this is now the estimator for the quantity of interest rather than the original estimator, which was simply 1 over n sum of g of xn. Yeah? And the proof is straightforward. It's basically the calculation above in terms of sample. So this I will leave to you to decide to do. The variance of this now g prime rather than the g of n that we had earlier happens to be 1 over n times the variance of g bar with respect to p. And this leads to the same heuristic that we can minimize it by choosing p to be close to g times f, and so on and so forth. So this is what is called importance sampling, in the sense that you are giving importance to the areas of your space wherever g multiplied by f are non-zero and other areas are deemed to be non-important. And that is one of the ways to look at why this is called importance sampling. Yeah. So p of x is non-zero where g times f is non-zero, and hence that's the important part. The remaining parts are not important, so forget about them. And the only thing to take care of is that now, by the way, these things are called weights. So g of x is what was the quantity of interest multiplied by w, and then w is called a weight. And w is just the ratio of two probability densities evaluated at the sample points. Okay, so translated into the language of filters, we talked about Kalman filter. This is exactly what is called a particle filter. Now, so effectively, the idea is that instead of, remember when we talked about ensemble Kalman filter, we simply had an ensemble, x1, x2, xn, say capital N, and then of course it had a index analysis of forecast A or F, and it has additional index T for time. Things start getting out of hand, the indices start flying all over the place, but the idea is still the same. Instead of having an ensemble by itself, x, I, T, F, we attach to each ensemble member the weight. A weight which effectively is the weight that is the representation of the density that you want to sample F divided by the density that you actually are sampling from, which is P. Remember, this was P of x of n, what is supposed to be P of x of n, right? So the weight will be the density that you want to sample divided by the density that you actually happen to sample. So that's what is represented by the weights in a particle filter. And these are called, so these are called particles now, not ensemble members. Each bit of this, each one of these is the weighted sample. Each member of it is called a particle. Why particle? I don't know. Okay, so the ensemble Kalman filter, we said what to do with this, right? Apply a certain algorithm to each of the particles, or the deterministic ETKF, or whatever else that you want, but essentially deals with ensembles. Particle filters deals with weights. So one way to think about it is as follows. I actually had a nice picture and then I forgot to include it. So I have the state space in which all the dynamics is happening. The ensemble Kalman filter deals with an ensemble of points and the probability distribution that this kind of ensemble will represent, let's say Gaussian distribution or something like that, right? all of them are as important as any other point. Each point is as important as any other point. That is, they are democratic. Each one gets the same vote. Particle filter not only gives you the position of a particle, assigns a weight. So I can now draw, let's say, a little bit of ball around each one. So if this one has more weight, I can put a bigger ball than say this, which has a smaller weight. And let's say this one is very big, and let's say this one is small, and so on and so forth, right? So for each one of them, now I can assign a weight, and the weight kind of indicates how important that point is, or the ball, the radius of the ball will indicate. This is a visual representation. And the way to do computations with this is that instead of computing the mean, I did not put that formula on the slide, did I? Oops, sorry about that. I thought I did. Okay, so it was 2 slides ago, but not in terms of these particle filters. So essentially, if you want to compute, say, the mean or any other quantity, you have to multiply by the weights appropriately. So wherever you see, say any quantity that looks like this, summation over I goes from 1 to P, the ensemble size of G of Xi, and then there is a time and forecast or whatever it is. Instead of just doing this, you multiply it by the weight associated to each of these particles now, and 1 over P, and that's the formula now for computing the averages. So if you want to simply compute the mean of this ensemble, it's not just the sum of all the ensemble members divided by P. You have to multiply by the weight, and that's the formula. Yeah. So and that's the visual representation is basically this, that different particles get different weights. The one that have very small weight will basically drop out of the sum. If W is close to 0, that particle will not really contribute much to this. So this is weighted democracy, preferential treatment, and so on and so forth. Yeah, but so that's the idea behind particle filter. So now the idea is, how do you deal with the prediction and the update step? What do you do at the prediction step? What do you do at the update step? The prediction step simply remains the same. That is, each particle, you apply the model, right? So this is simply applying the model dynamics, which is or forecast. Right? So that part remains identical to ensemble Kalman filter. The forecast step is the same. Take each ensemble member, go forward in time with the model, and you get to the next time. So you get basically the analysis. Sorry, suppose in order to go for forecast, you want to start with the analysis ensemble. What am I saying? Okay, so you have an analysis ensemble at time t. You do a forecast to get to time t plus 1, right? And that forecast is identical step as for the ensemble Kalman filter. The difference is at the time of update. When you want to update, the update is done by not, so one way to visualize ensemble Kalman filter is as follows. Oh, there is no ENK formula anywhere on the board, but it's on the screen, right? So if I have XIF at some point, what does the equation under the ensemble Kalman filter say? XIA, the analysis ensemble member, is equal to XIF plus something, something, something. So I'm basically shifting the particle from here to someplace else, and it will be XI analysis. Right? This position of the particle in the phase space, in the state space, will not be the same as this. There is some shift, and the shift is given by Kalman gain times the innovation, and so on and so forth. Yeah. So every particle goes through a shift. So if you have an ensemble of particles here, they may all shift to an ensemble of particles over there. Typically, this will happen by something like the observation is somewhere in that direction, so all the particles will kind of move towards observation. That's the intuition. In the particle filter, though, we are not dealing with changing X at all. the XIF is equal to, sorry, XIA is equal to, I didn't write it down. Okay, so it's all, we just change the weights. XIA is equal to XIF. The particles don't change, the positions don't change, the weights are updated, which means that a physical representation or a pictorial representation is as follows. Let me use the same picture over here. So suppose this was the ensemble that I started with. Right? So this was the weighted ensemble. These particles have high weights, these ones have small weights, and so on. And my observation happens to lie, say, over here. And observation has an observational error covariance, which can be represented by something like this, some small observational covariance. So this is the P eta. The P eta is basically the likelihood. If this was done in the last lecture, it's written over there, right? The update step is the product of the forecast probability and the observational likelihood. The probability of the observation given a state, that's the likelihood. So if the observation is here and P eta is basically, let's say, Gaussian with covariance which will taper it down beyond a circle like this, a ensemble member which was sitting here, which has a high weight, multiply by a factor which is proportional to the distance between the two, will now give you a WA, which will suddenly become significantly smaller compared to, say, the weight of this particle, which is going to be proportional to the distance between these two, which is much smaller than the distance between those two. So remember, a typical form of P eta for, let's say, Gaussian distribution, it's something like the P eta of y given x will be e to the power in one dimension it will be this, in high dimensions it's basically similar kind of, right? So it depends on the distance between the particles. So the farther the particle is, the farther the x is in that formula, the smaller the value of P eta and exponentially smaller, significantly small. So the difference between these weights is now, so to say, countered by how far the particle is in the observation space from the observation. Of course, since h is not exactly in the same space as x, I should really be writing this as y minus hx, right? So, yeah. And now we can see that what will happen, so all of these particles will get a tiny weight, so they will suddenly become small as in the analysis ensemble, whereas the particles that are nearby will get large weight. And the weight is now represented by the area of the circle I'm drawing around each particle. The positions don't change, only the weights change. Many times what happens is, so as in example like this, so suppose only 2 of the particles get large weight, everything else gets tiny little weight, 0. So effectively 0 weight particles do not add to the mean that we are trying to compute. I raise the formula for the mean. Sum over Wi g of xi is the formula for the mean. If Wi is small, all of these little particles over there, they're pretty useless. Why should I carry them around at all? I should really just throw them out. And that is what is called resampling. When you get lots of particles with lots of small little weights, don't keep them with you. Throw them out and only keep the particles which are high weight. But what will happen if I keep doing this? I start with the ensemble size 100. Suddenly after, they say 5 steps, many of them, the 5 of them get small weight. I throw them away, 95. After some time, maybe I will throw another 10 of them away and keep doing this. After a few time steps of observation assimilation, maybe I'll be left with only 10 or 20 or 50 samples. So my sample size will keep decreasing. Not a good idea because we saw that sample size has a very important effect on, for example, the uncertainty and so on, the estimates and so on, right? So we don't want to keep decreasing the sample size. So what's one way to go around not decreasing the sample size? And this is what is called resampling. So one way to get around this problem of if you keep throwing away particles with small weight, you will decrease the sample size. In order not to decrease the sample size, you resample. The idea behind resampling is that, so suppose now you have an ensemble of size 2 with weights which are W1 and W2. So of course W1 plus W2 must be equal to 1 because the weights have to add up to 1 and so on. Okay? So it's a normalized ensemble. Now with two ensemble members, I can't really do much. I want to now generate 10 ensemble members along with this. One way, so this is now, there are about 25 different methods of resampling. I can only kind of give heuristics behind what the methods do, which is that something that is nearby in say distance in the phase space should get slightly a weight that is proportional to that. So that's one way to resample. You resample point that is nearby and give a weight that is proportional to the distance to this particle. And that's one way. The other way is to simply keep doing this again and again. That is, you resample, you generate, so suppose this was 0.8 and this was 0.2. One way to generate, and so I have a sample size 2, I want to go to sample size 12. So I want to get 10 more particles out of these 2. One way to do it is to choose 8 new particles at the location of this one. So this is x1, and only 2 new particles at the location of x2, because that is proportional to the weight of each of these particles. So the total ensemble size now is 12. This one, these 2 remain with you. This one gets 8 particles, this one gets 2 particles, so to your total of 12 particles, such that now if you plot a histogram, where will you get the highest mass, higher mass for the histogram? Near this particle, because there are 8 particles here, 2 particles here, so the histogram will, so that's the main idea behind the resampling, which is according to the weights of each of the particles that you have kept. And then there are multiple other ways to, so I can actually, there is one nice paper which talks about 4 most commonly used, 4 or 5 most commonly used resampling methods. And so there, yeah, okay, anyway, I don't really have the time or the right background to talk about resampling in all the details, but the idea is as the number of particles with smaller and smaller weight have to be thrown away, you have to get new particles, and that process, so you have to create new sample points, and that's why it's called resampling. Yeah. Okay, so this is basically one slide summary of particle filter. That if you have the weights at time t, the weights at time t plus 1 are proportional to the weights at time t times, and this factor basically comes from looking at what these densities are. We want to sample out of this, we have a sample out of that. This is the factor, remember this was the factor that, this is the density that we actually want to try to sample. And the W, the weights, were proportional to F by P. F was the density we want to sample, P is the density that we actually sample, and that's exactly this ratio over here. This is the density that we want to sample. Q is what is called, as now I have put the word here, important sampling density. Q is the important sampling density that we actually happen to sample. And so this density we want to sample divided by this Q is the factor that goes into the weight. Right? So this is exactly parallel to the weight formula that I wrote down here with a typo that I will fix. What happened? Nothing changed. Oh, nothing changed. Oh, there, yeah, now it is changing. So this should be P. So so that formula is exactly F by P in slightly disguised notation, right? And that's the one slide, 2 slide summary of particle filter. There is a lecture on particle filter actual applications next week. By the way, the choice of this important sampling density is also, so there are 2 main key difficulties in implementing particle filters. One is how do you choose this Q? How do you choose the importance sampling density? One common choice is simply that Q of x is just the model. That is, it's a stochastic version of the model itself. That's the very commonly used importance sampling density. The other difficult, or the other main choice to make is how do you do resampling and when do you do resampling? And so importance sampling density and the resampling are the two places where all the different particle filters differ. And there is about 1 million of different particle filter variants. And each of them has a different choice of importance sampling density and a different choice of resampling for particles that need to be thrown away. So, okay, I think that's ETKF localization, particle filter, the modular code, the last bit. So I will take 5 minutes and do that. Sorry? You have to leave, I know. So yeah, thanks for yeah. Oh, no, please, yeah. Thank you.
Thank you.
Yeah.
I'll keep in touch.
Yeah.
Thank you all. Wish you
Yeah,
all the best.
thank you. Thank you.
Nice to know you. We will keep in touch. Bye-bye. Sorry.
Of course, yeah. Okay, so one thing that he requested is what about what parts of the code can be used and how to build. So suppose you have a model that's with you. How do you choose the initial ensemble? Okay, that's not easy to do. And we discussed a little bit about what the difficulties could be. There will be a lot more, hopefully, discussion when you actually see what people do in practice next week. There are at least two hands-on sessions, and you will get some flavor for that. The next thing is how do you do forecast? The forecast is the simplest case, I think, because the forecast is simply use the model to go forward in time. So the forecast bit that appears here, you simply replace it by the model that you have with you. The next bit is the analysis. The analysis can be multiple ways. One is, of course, the one I showed, which is the perturb-orbs analysis method. Almost nobody really uses it, I think. I don't really think after. So initially it was realized that they tried to implement the ensemble Kahneman filter without a perturb-orbs, It kept failing. That is, it kept giving these answers that if you run it for sufficiently long time, it will be highly precise but highly inaccurate. The filter failed. Then they realized theoretically that that was a problem. Theory has uses. That of course there was this missing K transpose term that need to be incorporated. One obvious way of doing it was to incorporate perturb-orbs. So it kind of works, but once you start doing this for very large models, this becomes difficult to do. Or very large number of observations, this also becomes difficult to do. So not a good choice. So then people went through this kind of, again, theoretical calculations of can we invent a transformation on the phase space, on the ensemble space, such that we get the desired formula for the actual ensemble, the desired formula for the analysis covariance, and that's the ETKF. I don't have a code for ETKF working right now. I tried to do it, it didn't work out. So, but it's not a bad exercise to try to devise. So I hope at least one or two of you can do this, or maybe a group of you. You can work together and write a replacement of this bit, which is a perturb-orbs ensemble Kahneman filter, by a ETKF. I erased the ETKF formula. It was straightforward. Remember that matrix V transpose plus identity inverse. It's a very simple matrix to construct from everything that's in the code. You construct that matrix, do eigenvalue decomposition, find the square root of the eigenvalue. The formulae were all written down there. I have uploaded a paper. I have given a reference to a paper, which I will upload the PDF for soon. That had all the details exactly in the same notation that I wrote down. So exactly translate the mathematics, the equations that are in that paper into the code, and write down a ETKF, a working ETKF code. The only place where you will need to worry about is how do you incorporate localization. And that's a bit tricky, but not that difficult either. So for next week, before before you have the weekend to work on this, no? Weekend is enough for doing this, because all you need to do is to literally replace these 5 lines with maybe a 10-line code, because you need to construct that matrix, eigenvalue decomposition, find a square root, multiply by z, and you're done. Okay, so by Monday this should be ready. Yes? No?
And Tuesday you are going to come back.
And I'm coming back. So I'm not
to
leaving you
verify.
like,
Yes.
I will be back here on Tuesday. So hopefully I will get one ETK working code by next week. Yeah? And let's see, then we can play around with that and see how that works compared to the perturb-ops code and so on and so forth and whatnot. Okay, so basically if you want to build a working system, the difficult part is, for example, how do you efficiently forecast things? So parallelization, for example, you really want to use parallelization. You don't want to use this. Right? So you want to do this in parallel. That's one choice to make. Analysis computation also in parallel, because for large system you can't just do it this way. And then there are tricks of the trade, which is if you have observations which are uncorrelated, you can simultaneously in parallel assimilate those observations which are uncorrelated, and so on and so forth. So there is the remaining parts are basically computational technical details. All the conceptual bits are all here, but the computational bits are non-trivial. They will take a couple of years to develop. So going from here to a working code for a large-scale system will take at least a couple of years. I don't know. Is that a reasonable estimate? Anyway, so yeah, so it's non-trivial. The technical details are non-trivial, but hopefully the conceptual bits are clear by now. And yeah, okay. So I think I'm done. Thank you.
Thank you. Any questions?
One thing I will put in the slides before sending it and sharing it with you guys. I will put in the equations corresponding to ETKF in the slides as well, so that they are all there explicitly, so that you can start writing your code. Okay, that's why. Okay. I'm doing my homework. You should do your homework.
Thank you, Amit. That was excellent lecture series. Let us thank Amit for his excellent lecture.
Thank you.
Thank you so much.